We're going to continue to talk about chi-square testing today. Before we get into what's new today, I just want to kind of recap what we did last class. So last class we were talking about chi-squared goodness of fit test, and a chi-squared goodness of fit test deals with a one-way table. So this was the example where we saw the percentage of cars by color that are in North America, and then what we observed in the Oro Valley. Then we went ahead and we found our expected counts by taking the percentage times the overall total. Remember, we don't round the expected counts. We went through the process of writing our hypotheses, checking our conditions, running the test, which is a chi-squared goodness of fit test, or GOF, on the calculator. And then we went ahead and got our conclusion based off of the p-value. This was a goodness of fit test, which we used for a one-way table. Keep that in mind as we deal with today, which is chi-squared test for homogeneity and for independence. So, a chi-squared test for homogeneity is used to compare the distributions of a single categorical variable across several populations or treatments. Key thing here is that data is going to be presented in a two-way table, which is different from the previous example we just saw where it was a one-way table. We were only measuring one variable, car color, for that one population. When you're writing hypotheses for a test of homogeneity, use the stem of the problem. So what does that mean? That means frequently it's going to look something like there is no difference between blank and blank, and then your alternative hypothesis, there is a difference. But again, the stem of the problem will guide your hypotheses. Something that's different and very important for these chi-squared tests is how you find your expected counts. And you'll see this when we go through our example, but to find the expected counts, you're going to take the row total times the column total divided by the overall total. And that'll get you the expected count for each individual cell in your table. Conditions, similar to what we saw before, your conditions for chi-squared test for homogeneity, random sample, or you will see problems that are random assignment. So it's that same randomness condition that we've seen in the past, but you just have to make sure that you're clear on what type of randomness it is. Second condition, all expected counts greater than or equal to 5. Your chi-squared test statistic formula is the same that we saw in goodness of fit. Chi-squared, which just is like a fancy X, it's a Greek letter chi, is equal to sigma, which means the sum of all of your observed minus your expected squared divided by the expected. So if you were to do this by hand, it would take a long time. Degrees of freedom is also different, so this is important. Frequently, multiple choice questions ask you about degrees of freedom. So to find the degrees of freedom for this type of chi-squared test, the number of rows minus 1 times the number of columns minus 1. And again, we'll see this in the example. Use your calculator. Chi-squared test, which is C, on the calculator will be used here. So, if we are going through this, and again, like I said, we're going to be running a chi-squared test, which is C, on the calculator. So here's our example. It says, how is the hatching of a water python influenced by the temperature of the snake's nest? Researchers randomly assigned heavily laid eggs to one of 3 water temperatures, hot, neutral, or cold. And then we measured whether the egg hatched or not. So we want to see, is there convincing evidence that temperature affects hatching status? So this is what we've got a two-way table where we've got hatching status, yes or no, that's one variable. Cold, neutral, or hot, that's our other variable. So we know that it's a chi-squared test. To use a chi-squared test, we're going to have to enter our data into matrices on the calculator, which is the most annoying part of this type of test. In order to enter the data into the matrices, that's going to be under second and inverse X. And then we're going to have to go to edit to do that. You're going to enter your observed into matrix A and your expected into matrix B. And you don't enter in the totals. So these numbers here won't be entered. Just each of these cells are going to be entered there. So in order to do that, we have to find our expected counts first. So you have to find the expected count for each individual cell here. 1, 2, 3, 4, 5, 6. When I'm doing this, I usually make a separate table of my expected counts. And you have to show your expected counts, and they should be labeled. Some people will write them right next to them here, but it's going to get a little squished, so I just make another table. Yes, no, cold, neutral, hot. So to find this expected count for this cell right here, we're going to take our row total, which is 129, times our column total, which is 27, divided by the overall total, which is 187. And that's the work that I've shown right here. 129 times 27 divided by 187. If I do that, I'm going to get 18.63 as my expected count for the cold and yes. And again, just like expected counts in the past, don't round these to whole numbers. For neutral and yes, I'm going to take 129, my row total, times 56, my column total, divided by the overall total of 187. Keep going. Yes and hot, 129 times 104 divided by 187, and I get 71.74. Keep going through this process, and you'll get the rest of them, which I've shown the work for here, 8.37, 17.37, and 32.26. So now that you have your expected counts done, now you could go through running the actual tests. So in terms of our hypotheses, what are we seeing if we have evidence of? That's our alternative hypothesis. We're seeing, do we have evidence that temperature affects hatching status? Our null hypothesis, temperature does not affect hatching status. Once I've done that, I can check my conditions. So my conditions, this case is randomly assigned. So make sure you're specific about it. Don't just put random. Don't just put random sample. This is random assignment. And all of our expected counts, these guys, not the observed, the expected counts that we just found have to be greater than or equal to 5. That's why it's important to label them. Because if you just show this and you just say all expected counts are equal to 5 without specifying these are the expected counts, you will not get full credit. All right, so we've done our conditions, we've done our hypotheses, we know we're running a chi-squared test. So now it comes into the calculator. So on our calculator, we're going to go to stat. Oops, sorry, not stat. We've got to enter our data in first. So we're going to go to second and inverse x, which is our matrices. We're going to arrow over to edit. And first we're going to do matrix A, which is our observed counts. So these ones up here. We've got to deal with the size of a matrix. A matrix is sized by the number of rows times the number of columns. So this would be a 2x3 matrix. And again, you don't enter in the totals into these matrices. Now we're going to enter in our observed counts. So the 16, the 38, 75, 11, 18, and 29. So my observed counts are in matrix A. I'm going to go back to second and inverse x, arrow over to edit again, and now in matrix B, I'm going to put in these expected counts that I just found here. So that's going to be my 18.63. Oh, again, I have to change the size of the matrix. My 18.63, my 38.63, my 71.74, my 8.37, my 17.37, and my 32.26. So my expected counts are in matrix B. After I've done my two matrices, I could run the test. So stat over to tests, and I'm going down to letter C, which is a chi-squared test. Last class, we did chi-squared goodness of fit. This is just a regular chi-squared test, C. Don't have to change anything here. Matrix A is my observed. Matrix B is my expected. Calculate or draw, doesn't matter which one you do. And I'll get my chi-squared value, my test statistic, and my p-value, as well as my degrees of freedom. So my chi-squared value here is 1.70. My p-value is 0.43, and my degrees of freedom is 2. And again, I got these degrees of freedom by taking the number of rows minus 1, which in this case would be 1, times the number of columns minus 1, which would be 2. So 1 times 2 is 2. Now, you'll notice this chi-squared value is pretty small, 1.70, because our observed counts and our expected are all pretty close to one another. 16 and 18.63, 38 and 38.63, 75 and 71.74, and so on. So when your observed and your expected are close to one another, this chi-squared value is going to be pretty close to 0, all right? And that means our p-value is 0.43, is pretty high. So compare your p-value to the significance level. They didn't give us one, so we'll still use our common one of 0.05. 0.43 is greater than 0.05, so we're failing to reject the null hypothesis. So we can't reject this, could be true, but no evidence of the alternative. So final thing, conclusion and context, we do not have convincing evidence that temperature affects hatching status. And that's a chi-squared test for homogeneity. Pretty straightforward, okay? Just a little bit more time consuming than some of the other tests that we've run. If we keep going here, I want to briefly talk about a chi-squared test for association. Okay, chi-squared test for association. Well, what does association mean first? Association means that knowing the value of one variable helps to predict the value of the other variable. So your null and alternative hypotheses here are going to be slightly different, but again, use the stem of the problem. Null hypothesis, there is not an association or there is no association. Alternative, there is an association, and then include context. Next class, I'm going to talk a little bit more about the differences between homogeneity and independence. Key thing being homogeneity is one variable from two or more populations or treatments. Independence is two variables from one population. Expected counts are done the exact same way. Test statistics, same thing. Degrees of freedom, same thing. Conditions, same thing. Everything is done in the exact same way for a chi-squared test for independence as a chi-squared test for homogeneity. The difference is in the sampling technique that you've used to get your data. But everything else is exactly the same. On the calculator, it's the exact same thing as well. So I'm not going to go through this example down here, but you can write it in the notes if you would like to. All right? But this one deals with, is there an association between age and online banking? So null hypothesis, there is no association between age and online banking. Alternative, there is an association between age and online banking. You go through the exact same process, okay? Check your conditions, find your expected counts. You'll notice in this time, I just wrote them next to them, what each of them were, and I showed the work down in here. You'd go through the same exact process as you did in the past. In the last example, you would then go enter your observed data into matrix A, your expected, which is in the pink here, into matrix B, run the test, and you'll notice here you have a massive chi-square value of 43.80, which means that your observed and your expected are very far apart. P-value less than the significance level, rejecting null hypothesis in favor of alternative. Therefore, in this particular example, we would have convincing evidence that there is an association between age and the use of online banking. And again, we do this in the exact same way that we just did the last example. The only thing that's different is the name of the test. And in recent years, the AP exam has gotten more strict about knowing the difference between a chi-squared test for homogeneity and independence. That's all for chi-squared test for homogeneity and independence. See you guys.